I welcome you all in this presentation related with the subject failure analysis and prevention. And we are talking about the failure analysis of the steel components. So, in this particular presentation, we will be talking about what if the heat treatment is not done properly, then how the failures of the steel components can occur. So, initially we will be talking about the basics related to the heat treatment and the way by which things can go wrong if the incorrect the approach or the process or the parameter is selected. So, here this presentation primarily includes the heat treatment of steels where we will be talking about the scope and the purpose and the structure property relationship means how to adjust and regulate the structure so that desired combination of the properties is realized and then how the iron carbon diagram and continuous cooling transformation diagram are related with the heat treatment and how these two diagrams form the strong basis for designing the heat treatment. And then we will be talking about the basic principles of few heat treatments which will include like normalizing, annealing, hardening, then tempering, os tempering, mar tempering. So, through these diagrams we will try to quickly present the basic aspects and then we will be talking about a case study where in the failure of a component due to the faulty heat treatment has taken place. So, and the relevant the failure analysis observations and findings will be presented. So, you know that the steels are the steel is an alloy of the iron and carbon particularly, and other alloying elements are added to achieve the desired set of properties in case of the alloy steels. Okay. So, when only carbon content is controlled, then we call it as a carbon steel or plain carbon steel. The steels offer a very unique benefit in terms of the property alteration that by changing the certain phases, we can achieve a variety of the properties which can range from very soft and low hardness, high ductility to the high hardness and the low ductility or low toughness. So, depending upon the requirement of application, we try to adjust the suitable microstructure or microstructure of steel suitably so that we can achieve the desired set of properties. Okay. So, this is what is achieved effectively and easily through the heat treatments. So, heat treatment of the steel component is done for multiple purposes. One of the amongst those is like to achieve the desired mechanical properties. So, the goal may be to have the desired high hardness for wear resistance applications. Okay. So, abrasion and adhesive wear resistance is extremely good, or a goal may be to have the high toughness. So, we may go for like the fine grained structures with the moderate set of mechanical properties to have the high toughness and that will be offering you increased resistance to the crack nucleation and its growth. So, depending upon the requirement we can go for a variety of combination of mechanical properties and that is achieved through the suitable heat treatment of steel. Okay. We know that the components because of the structural changes experience a lot of change in mechanical properties when subjected to the heat treatment. Okay. So, there are two aspects like the high temperature, dimensional stability and high temperature and mechanical properties, you see. So, depending upon the requirement what is done, exposure to the component at the manufacturing stage is given in such a way that the component has the desired set of the structures as per the application temperature. So, that is what is done basically to have the desired mechanical properties even at higher temperature and likewise for the dimensional stability. So, the high temperature exposure is given actually for that purpose. Then we know that during the manufacturing process like casting, forming, welding, lot of residual stresses are induced and these residual stresses tend to adversely affect the mechanical performance. So, if the residual tensile stresses develop, then they compromise with the like tensile load carrying capacity and the fatigue resistance under the tensile loading. So, efforts are made to neutralize the effect of these residual stresses by inducing the residual compressive stresses. Okay. So, what is done once if the residual tensile stresses have been developed, then their magnitude is reduced through the heat treatment. So, that is called a stress relieving treatment. Alternatively, what we can do also, like if the component is not having any residual stresses, then we can make efforts to induce the residual compressive stress. Okay. So, to enhance the performance under the tensile loading or under the fatigue conditions subjected to the tensile loading. Okay. So, there are both possibilities. One, either residual tensile stresses are minimized or eliminated through the suitable stress relieving treatment, okay, or suitable heat treatment is done so that the residual compressive stresses are induced. Okay. If that is achieved, then our performance of our component is enhanced, and sometimes even the improvement in machinability of the high carbon steel is also achieved, especially in case of the hyper-eutectoid steels, the where we have the thick layer of the cementite. So, the thick layer of the cementite adversely affects the machinability. So, to improve the machinability of hyper-eutectoid steels, the spheroidizing heat treatment helps in improving the machining. If the heat treatment is being done is not of proper type or is not done under the appropriate conditions of high temperature exposure for sufficient time followed by the controlled cooling, then it will lead to the compromise in the set of properties that we are expecting. Okay. So, the heat treatment can also be done after the manufacturing and repairs to avoid any undesirable uh, effects which have been introduced in course of the manufacturing, or to achieve the desired set of the microstructure and mechanical properties in the component after the manufacturing and repair. Okay. So, the thing is this here, this is the iron carbon diagram. These are the two diagrams, basically iron carbon diagram, and this is the diagram which shows that the temperature and time relationship for dissolving the various constituents to form the homogeneous austenite, okay, for the heat treatment. So, if we see in the x axis we have carbon and in y axis we have the temperature, and this diagram, iron carbon diagram, shows this is a curtailed one, means not full range of the iron carbon diagram has been shown. So, what it shows, this is the upper critical temperature line and this is the lower critical temperature line corresponding to say 727 degrees centigrade. So, upper critical temperature changes with the carbon content, that is what we can see. It is for 0% carbon it is 910, and then it keeps on decreasing and reaches to 727 for about eutectoid composition, say that is corresponding to say 0.8%, and then again it starts increasing with the further increase of carbon content and the other various phases. So, when the heating is done between the upper and lower critical temperatures, then it is called intercritical temperature heating. Okay. Usually for normal heat treatment processes like annealing, normalizing and quenching, or even for OS tempering and mar tempering, heating is done above the upper critical temperatures, which is say 30 to 40 or 50 degrees centigrade above the upper critical temperature, so that all soft phases like ferrite, perlite or other constituents, if they are present, they can be dissolved and homogeneous austenite is found. Austenite being a metastable phase, on subsequently on the cooling, depending on the cooling conditions, it forms the variety of phases. So, desired phase is obtained through the controlled cooling in the subsequent stages, but that can be done only if all the soft phases and other constituents have been dissolved and homogeneous austenitic state has been achieved. Okay. In addition to these heat treatments where heating is done above the upper critical temperature, say upper critical temperature plus 30 to 50 or 40 degrees centigrade above this for achieving the homogeneous austenitic state. Okay. In addition to that, there are other lines like this is the tempering temperature line, or this is the range also for the our stress relieving conditions. So, the tempering temperature means say around 200 250 degrees centigrade to below the lower critical temperature, that will help um, in tempering the martensite and inducing the toughness, improving the ductility. Okay. And say around 600 from 200 to 600 degrees centigrade, also the heating is done for the stress relieving treatment purposes, so that the residual stresses can be reduced. Say 400 degrees centigrade is the recrystallization temperature for iron and the steels. So, say when the steel which is having say basically the iron and carbon, and depending upon the other alloying elements, you say other alloying elements, if they are there, it can have the variety of phases like alpha ferrite, alpha iron, others ferrite, then we can have the cementite Fe3C plus alpha ferrite iron, that is in form of say perlite. Okay. And then there is a possibility, depending upon the alloying elements, there is a possibility of alloy carbides. Okay. So, initially these are the constituents which are present in the steel at room temperature. What happens when the heating is done? Then as a function of time, alpha iron, perlite and alloy carbides, in if there are alloying elements and their carbides are being formed. Then above the upper critical temperature, how the things change as a function of time. Okay. If we take a high temperature, then these phases starts getting dissolved earlier, like say this is the, so initially alpha iron, perlite and alloy carbide. So, this perlite will be transforming into the austenite, alloy carbides will be there and alpha iron will be there. Thereafter, on further continuous heating, means for further longer soaking time, our the alpha iron will also be transforming and then into the austenite, and then we will be left with the alloy carbides. And thereafter heterogeneous, because alloy carbides, whenever they will decompose, alloying elements will get will be segregated near these carbide locations. So, what will happen? It will be forming the heterogeneous austenite. So, it further requires the higher temperature to get the homogeneous austenitic state. So, these are the different stages through which the various constituents will be transforming into the austenite. Okay. So, if we take the higher temperature like this, it will be taking shorter time. If we take the lower temperature like this, then it will be taking longer time to achieve the homogeneous austenitic state. Okay. Once the homogeneous austenitic state is achieved, we will be imposing the different cooling rates to achieve, to obtain the different phases. These phases may be in form of like coarse perlite, fine perlite, this can be benite, this can be martensite, or mixture of martensite plus perlite, like this. So, these are the various phases which are obtained. So, depending upon the kind of phases which have been achieved and their proportions, what will be having high perlite, low high ferrite, low perlite will be resulting in the soft, means the low strength, low hardness, high ductility, and fine perlite, fine ferrite and fine bennetic structure will result very good combination of the strength and the toughness and ductility. High yield strength is achieved when fine perlite, fine benite and fine martensite is there. High fine martensite, benite and perlite is there for high yield strength, and high hardness is obtained when we have high martensite and cementite, and high toughness is obtained when fine perlite, fine ferrite and the fine benite is present. Okay. So, here idea is to achieve these phases as per our requirement of the properties. So, this the first diagram is the triple T diagram, that is the temperature time transformation diagram, and the second one is the CCT diagram, which is continuous cooling transformation diagram. So, CCT triple T diagram, what it shows, what happens to the austenite when it is subjected to the constant temperature as a function of time. So, at a high temperature, the transformation of austenite starts into the perlite at this time, and then it ends at this time when the exposure is given at a constant temperature. So, what it will be resulting in the coarse perlite. Okay. When the steel is subjected to the lower transformation, lower temperatures, then what will happen? Say this temperature T is 2 say another temperature, a lower temperature, then transformation will start earlier and then it will end earlier, and it will be resulting in the fine perlite. The further lower temperature, say this is the nose of the diagram, and here what will happen, the transformation will start at the earliest and then it will end earlier. Okay, and on further lower temperatures, then this will start getting delayed, okay, and will be ending late. So this is why it results in the C shape structure. Okay, so and this is the nose where the transformation will be starting earliest and will be ending earliest. Okay, so what is happening, initially we get the coarse perlite, then fine perlite, then we get the coarse bainite and then fine bainite. These things happen at a constant temperature of the transformation of austenite into the other phases. Okay. So, accordingly, you see this will be increasing in the hardness. You see the minimum hardness is achieved when the coarse perlite, then somewhat greater hardness when fine perlite, then further greater hardness when coarse bainite is achieved, and further higher hardness is achieved when the fine bainite is obtained. On further cooling at lower transformation temperatures, lower temperatures, what will happen? We will be having, so there are two lines, one is the MS, that is the martensite start temperature, and martensite finish temperature, say this one. Okay. So, if we quench directly the steel from austenitic state to any of these temperatures, then accordingly the temperature at which we are quenching will be having combination of austenite and martensite. Above the MS temperature there is just austenite, and below this there is a just martensite, and in between the MS and MF there is a austenite and martensite. But these transformation indicate the transformation of the austenite into the other phases at a constant temperature. Okay. But most of the time heat treatment is done under the continuous cooling conditions, because it takes very long actually. If you see, these times are in the log scale. So, this may be taking very long to achieve these phases. So, usually in heat treatment is done under the continuous cooling conditions. So, we are just to say when continuous cooling conditions are imposed, then our diagram is little bit modified. We do not have the lower section here where the bainite is formed, because bainite is formed particularly at the constant temperature of the transformation. Okay. So, let us talk about the CCT diagram. So, what happens when the continuous cooling is applied? Transformation starts at TS1 and it ends at TF1. So, these two temperatures are different actually. So, initially it will be forming the coarse perlite, and then later on in the later stage it will be forming the fine perlite. Okay. So, the grain size will continuously be changing here in course of the transformation of austenite into the other phases, because the transformation is not happening at a constant temperature, but it is happening at the different temperature. So, if the cooling rate is this, then what will be happening? A part of the austenite will be transforming into the perlite, and remaining austenite will be transforming into the martensite. That is why what will be having here perlite plus martensite. And when the cooling rate is such that it just touches the nose of the curve, then there is no transformation of austenite into the perlite, only transformation of austenite into the martensite starts here and it ends here. Okay, which means you will have just martensite. This cooling rate is known as CCT, a CCR, critical cooling rate, and any cooling rate greater than the critical cooling rate will be resulting in the just martensite. Okay. So, depending upon the purpose and application, desired set of the properties are achieved. We may require just coarse perlite, fine perlite, or mixture of perlite and martensite, only martensite. Okay. If you want bainite, then different kind of the heat treatment is performed. Okay. Or for the alloy steels also there will be different kind of these continuous cooling transformation diagram, and we may get the bainite also in those cases. So, in simplified form, if you want to talk about the heat treatment steps, it involves first heating to the desired temperature, that is 30 to 50 degree centigrade above the upper critical temperature to achieve the homogeneous austenitic state. This time should be sufficient to achieve the homogeneous austenitic state. Thereafter, low cooling rate is imposed for annealing purpose, that will be resulting in the coarse perlite, and fine perlite is obtained. Little higher cooling rate is used for fine normalizing, that will be leading to the fine perlite, and we will be having further higher cooling rates for achieving the martensite for higher hardness. Okay, these are the three most common types of the heat treatment. And if the proportion of the martensite increases, of course, our hardness and strength will keep on increasing with the increasing proportion of the martensite, but this will be happening at the cost of our toughness and ductility. So, we know that when the hardening heat treatment is done, most of the time our austenite transforms into the martensite, and what martensite does is uh, it increases the hardness, okay, but badly compromises the toughness and ductility. Okay. So, to make the components workable for engineering application, what is done after the hardening heat treatment, again the steel is reheated. So, heating, austenitizing, rapid cooling, this is the hardening heat treatment. Then again steel is subjected to the reheating, and then this reheating temperature will depend upon the property combination that we are looking for in terms of the toughness and the kind of compromise in strength and hardness that can be uh, accepted. So, accordingly the suitable tempering temperature is selected, and this is always lesser than the lower critical temperature. So, what we do, we reheat the component in this temperature range, hold it for some time, which may range like 30 minutes or 1 hour or 2 hours depending on the section size, and then again it is cooled slowly. Okay. So, again the subsequent cooling will depend on the composition of steel to avoid the cracking tendency. So, simply air cooling can also be done. So, what happens when the different kind of the tempering temperatures are applied for the heat treatment purposes, usually the in case of carbon steels hardness comes down very rapidly, but in case of the alloy carbide secondary hardening happens. This particularly happens due to the formation of the tungsten carbide, vanadium carbide, molybdenum carbides, carbides of certain alloying elements which are formed at a higher temperature. So, the secondary hardening is observed in case of the alloy steels. Okay. So, this is about the hardness variation, and as far as the toughness variation is concerned, with the tempering temperature is like usually the toughness increases with the increase of the tempering temperature. So, depending upon the requirement, like say if you superimpose these two lines, then it will be coming like this. Okay. So, what kind of combination in properties we are looking for, like low toughness and high hardness, or a high toughness and low hardness. So, which kind of combination is desired for a given application, accordingly the suitable tempering temperature is selected. Os tempering and mar tempering are these two other important heat treatments. Os tempering is done primarily to form the bainite. Okay. So, what is done? The component is quenched just above the MS temperature, and it is held at that temperature for long. So, that whole austenite transforms into the bainite, followed by air cooling. This is what the aus tempering is. And in mar tempering, things are cooled rapidly just above the MS temperature, then cooled rapidly, followed by tempering in case of the mar tempering. So, here in aus tempering we get the bainite, and in case of the mar tempering we form the martensite followed by tempering. Okay. But here quenching is done again just above the MS temperature. So, the temperature across the section is homogenized to avoid the differential cooling rates being experienced and the different phase transformations, and also to reduce the distortion and cracking tendencies. This is done. Okay. So, this is a kind of the case study where we will try to see what if the heat treatment is done incorrectly, or incorrect type of the heat treatment is done, then what happens to the component performance. Okay. So, say the component was made of the low carbon steel, say a nozzle, the failure of the nozzle used for the spraying hot water. This is the component having nozzle machine having a nozzle which was being used for spraying the hot water for a particular application. This nozzle failed prematurely, and how it was judged, like the speed of the water jet which was coming got reduced, and that in turn affected the performance of the operation for which this hot water jet was being used, and therefore, the nozzle failed prematurely within 6 months of service, while the other nozzles were working successfully even after 2 years of service. So, when the investigation was conducted, and it was found that steel had lesser carbon content than the specified. This was one. So, incorrect incoming raw material. The steel composition through spectroscopy was analyzed and it was found it had lesser carbon content than the specified 1.45, which means this would be having high proportion of the ferrite and very less proportion of the perlite, okay, as compared to the one which would be there in the 0.45% carbon steel. Visual examination, what it suggested, enlarged hole size. Okay. So, that suggested like the wear of the nozzle has taken place and that the wear was not irregular. Initially it was circular, but after the erosion it increased. So, the dimension of the hole of the nozzle increased and the shape became irregular. Okay. When the mechanical properties of the nozzle were examined, it was found that it was a half hardness 10 HRC as compared to the specified 22 HRC. Microstructure study revealed the coarse perlitic and the ferritic structure instead of the fine grained structure. This structure suggested the annealing heat treatment instead of the recommended normalizing heat treatment. So, there were two issues. One was like lower carbon content and the incorrect microstructure resulted from the inappropriate heat treatment. Okay. So, we know that when the nozzle being used for spraying the hot water jet, during the operation this frequently comes across the cavitation condition. And cavitation, how does it occur? Initially the surface is see what happens, like under the cavitation conditions, initially vapor bubbles are formed and they will be bursting at the surface of the nozzle and creating high pressure shock waves. Pressure can go from 1000 to 1500 MPa. This will be resulting the surface layer plastic deformation. Okay. Continuous pressure shock waves result in the pits which are smoother at the surface through the removal of the material. So, initially the surfaces may be smooth and there won't be any wear or erosion, but after some time if we see the cavitation and the wear happening due to the cavitation as a function of time. So, this is the time when the cavitation will be starting, it is known as incubation period. Okay. And thereafter the cavitation or the wear will start, okay, and then it will continue to increase. What it requires, like a good combination of the hardness and good combination of the ductility, that's toughness. Okay. So, a very good combination of the hardness and toughness is needed, but these two are opposite properties. If your hardness is high, toughness will be low. So, what we do, we try to optimize an optimum combination of the hardness and toughness through the fine grained structure and suitable combination of the various phases which are there. So, the further investigation revealed that there were no defect whatsoever kind in the nozzle, means only the surface irregularities and the cavitation effect was observed at the surface in form of irregular hole and the enlarged size of the hole, and it did not reveal any kind of the defect. And the operation was also like normal operating conditions were observed without any like previous repair kind of thing. Stereoscopy and SAM images of the worn out surface revealed the deep craters, pits, lips and the deformed surface layers. These are suggesting the possibility of the cavitation erosion. Okay. This cavitation erosion primarily occurs when the hardness is low and the toughness is also low. So, a comparison of the nozzle failed in the initial stages of service with the other nozzles installed almost at the same time that continued to perform even for the 2 years. This suggested like there is something wrong with that nozzle. So, what was done? Investigation, what it suggested, like the percentage of the carbon content in the steel is low, like it was 0.2 instead of 0.45. Okay. and the structure was coarse, perlitic and ferritic rather than fine uh, ferrite and the perlite. So, this structure was basically the dominated by ferrite and the less perlite, otherwise the structure should have been dominated by the perlite and less ferrite, but fine one. Okay. So, this suggested the possibility of incorrect annealing heat treatment, and that was reflected from the coarse perlite lower hardness thing. So, the incorrect heat treatment resulted in the coarse perlite and the coarse ferrite, and also the lower hardness. So, these were the main regions. Also, the carbon content was less. So, all above suggested that the failure of the nozzle by cavitation erosion due to the improper material composition, lower hardness, improper structure and the incorrect heat treatment that was applied. Okay. Now, I will summarize this presentation. In this presentation, basically I have talked about the various heat treatment processes, the basics on which the heat treatment of the steel is based, and one case study on the failure of the steel nozzle which had taken place. So, investigation suggested that the carbon content was low, the structure was not appropriate, and the heat treatment which was done was also not proper, and that resulted in the lower hardness, and that in turn totality resulted in the reduced cavitation resistance, and that in turn led to the failure of the nozzle. Thank you for your attention.